so many people actually never even cracked the guide to files, and let alone cracking the real McCoy, the Kirby McCoy, right? Because that's the Bible as far as the file system, both on disk and internal actions. We are only going to cover on disk, but the internals are way more. So quick overview, do my introduction, talk a little bit volumes, then get into file naming, basic concepts of a volume, a file, and so on. And really this talk is about index f.syst, which is the one file you don't know about on the box, but it ties everything together. And then the non-goals, I'm not going to talk the runtime, I'm not going to talk about ODS5 details, whether it's 236 bytes names or 288, I don't care, kind of. Symlinks, extended file spec, related file name parsing, very interesting topics. I could fill an hour on related file name parsing, but let's not. Rooted directories, same story. They're there, and that's just the next level. And let's see. So for that other audience, this is not Unix, right? So we don't have that single starting point / the top of everything, and you go down, and there might be a mount point in the middle there, but you don't care because it all looks the same. So no easy forward slashing to parse. We have our special parsing that needs to be done, recognizing a device part, recognizing a directory and subdirectories as appropriate, and following that up with file names and extension stuff. So for us, empty file name extension, I don't know why I put that there. And no hard links, making multiple paths indistinguishable, although symlinks get close, but they're not like hard links. And when we do the set file / enter, we can make, it's hard to tell the difference between the original and the link that you created. So the file system is a little bit more similar, to Windows, I think. We have the drive ladder to begin with that Windows also have. One big difference that we can all handle the file naming, of course. That's just a matter of learning. There's also one big difference is a feel and how you use the file system and the commands that you can get away with. If you do a dir/date greater than yesterday on a VMS box, it will take forever. ... If you descend the tree and you look for a date, right? Because VMS, as you all know, Unix stores those attributes in the inode, and as it sees the file, it sees the dates. But on VMS, when I see the file name, I have to go to the header, and in the header, I'll find the date. And that's an IO, a random IO. The next header is not going to be next to it. It's going to be in a completely different space. So if I visit 100,000 files, I'm going to do 100,000 IOs. That takes a minute. Well, no, it takes 12 seconds or something like that. But it's different from your Linux experience. Documentation, there is quite a bit of documentation. The hard definitions are, of course, in the Kirby-McCoy book. There's no explanation why things are the way they are. And maybe that we talked about it earlier also, similar with RMS. We are very welcome, able to tell you the bits and the bytes, but we never explain why the bits and bytes were designed that way in the first place. And that's kind of, Andrea and we were talking about a training in that direction, right? Internals, but also why it is the way it is. If you go, actually, I was surprised to find the book online. So if you Google for VMS file system internals, you will get a PDF to the book, and on BitSavers, magic. And you even can find, if you look a little bit more, you can find Andy's original 1975 definition of the ODS.
Did you bring signed copies of the book for us in the back of the room?
No. So the Guide to File Applications is a fine book. There's quite a few details in there, and you should really follow that. there's a dedicated guide to file specification, and another 100 pages or so. And then in the OpenVMS concepts manual, if you look around for this couple of sections on file operation, and again those extended file specification. And even Wikipedia knows a little bit about files 11. Yeah. Why not? All right. Let's start at the top. The top, you have a device to plant your files on. The device is a block, something of block addressable storage, whether it's in memory or physical disk or that old floppy, so to speak. But it's just a series of blocks that you can point to, and you can ask for one block. It doesn't have any structure yet. So on the VMS side, we call those logical blocks. To make a distinction with the virtual blocks within the file, logical blocks are on the disk. I'll repeat that a couple of times. The virtual blocks are in the file. Once a volume now is a device that has been initialized with a file system, the ODS file system in our case, right? So we in your directory, in your file specification, they look the same. DKA, Hein, test. The DKA is both a device and a volume often, so they can be a little bit confusing. So in our case, we put the ODS2 or ODS5 on this structure in place, and we mount the device, and now it becomes a volume. And I didn't know where to put this in the presentation. I want to get it out of my system. This notion of cluster size, where that device is allocated in blocks. When we allocate a file on a volume, we don't allocate in blocks, we allocate in clusters. Each cluster is represented by a bit in bitmap.sys. I'll show that at a later stage, and that indicates whether the block is free or not. So if we need a bunch of free space, we go into bitmap.sys, we look for a bunch of clear bit or set bits, I forget which way around it is, don't matter. And that's how we know what we can give out and what's already in use. Those clusters of blocks that we deal with, they have a given size. You can pick a size. The default is mostly 16 these days. The maximum is either 16K or 1/5 of the volume size. That's the rule of this. I don't see people using 100,000 block clusters, but could. If you have a terabyte drive and you're going to put five files on it, and they're all going to be 200 megabytes or gigabyte, then why would you muck with 16 block clusters? So the way I interpret that is what is then the best cluster size? Well, that clearly depends on your application, as always. Maybe to give a guideline, and I'll take your feedback on that. I would say if you have a few larger files, like less than 1,000 files, and there are more than 100,000 blocks, go big. Why not? Well, why not? Because you could potentially waste the last cluster, right? We allocate 500 clusters for the file, and the last cluster, the file needs not all of the last cluster. It might only need one block in that last cluster, and all of those 2047 blocks would be wasted. But now we're talking about a device with a million of them. Right? It don't matter much. Not if you have only a few thousand files. If you have lots of little files, let's say more than 100,000 files and they're less than 1,000 blocks, which is on the system disk, you have those little error log things, and then the SSH and the telnet 5 block files that are just popping up all over the place, right? Then you don't want to go too big. What do you guys feel about those numbers? Do you use 2,000? Does anybody use like a cluster of? I don't think anybody does at this point. I think people are holding back.
My backup disk is 8192.
81, okay, so
For my backup
even more.
disk.
Yeah, because you're only going to have.
I know my backups are huge.
Correct, and that's going to be it. The disk can be filled with these huge files, 2 gigabyte or whatever they are.
Yeah, my log disks tend to be 32 or 64,
Yeah.
depending on the size of the log files.
But I think 16 is still on the small side. It makes the system do more work than necessary.
Remember when they were 3?
I know. And I remember when they were prime numbers. Somehow we decided that prime numbers was the right thing to do. That's long gone from the code, but yeah, I didn't get that.
It does seem like in user experience, they're often smaller than they should be.
Yeah, I think that's the big message, guys.
Yeah.
Go big. Your disks are big, your files are big, the cluster should be big. Anything else over. So I said we transitioned from a device to a volume, and we put a structure on it. There's 2 structures available today, the ODS2 and the ODS5. Why would what do I pick? Well, the big difference is in the file naming rules. So I guess these days you should just pick ODS5. There's really no reason not to go there. There's slightly different on-disk structures to handle those big file names, and to handle symlinks sitting there too. So the main difference is the file naming rules. That's how I interpret the difference. You can convert the volume from ODS2 to ODS5 on the fly. It's a one-way conversion. If you really want to use ODS features, the first step is to set process parse status extended. Now you can fully use those long names and the multiple dots in the file names.
So there's no chance of corruption with doing the set volume sign structure?
We've had no reports of that.
Okay.
Oh,
yeah.
You can get
Well, I would assume that you couldn't.
And yeah, you can. Once you have a large file, then you get there's a message. I forget the message. You can't mount it anymore. So the big difference, the traditional ODS2, the file name and the file type can be 39 bytes, and only alphanumeric characters, dollar underscore and dashes are allowed. No funny characters. File names are not case sensitive. In fact, they're stored as uppercase file names, and you type in any which way. And it takes years to get used to seeing a lowercase file name show up when you just thought you created a file. It looks messy to me in my directories, if you like, but I'm getting the hang of it.
I feel like I've done something wrong.
Yeah, yes. I'm not alone in that.
I have the impulse to fix it so it's uppercase.
Yes, I've renamed files to make them be uppercase after all, because I feel at home with uppercase file names.
Well, it's also annoying when VMS will find the file if it's lowercase.
Yeah.
But Linux does not.
It does not. So
Linux says those are 2 different file names.
And they will be once you go extended. So in ODS5, the file extension and file names can be 236 combined. This was the last thing I read. I hope that's the right number. And we support a larger character set. Case is preserved in the file name. The biggest one is the file can contain multiple periods, but they have to be escaped to make it visible with a caret to show that what it is. And so it allows for oops, let's go back. It allows for file names with multiple extensions, similar to Perl.12.4.zip, and that's what they like to write.
So how does that still apply with, like the node name, colon, that whole spec?
I don't know. I didn't think of that for the purpose of this presentation. I do know that we want to discourage the whole DECnet thing, but that's a different story. Because it's an insecure protocol on the wire. Anybody with a wire sniffer.
And they're turning it off by default.
Yeah, we're turning it off. So let's go back. So I jumped ahead a little bit. I already tossed around things like file name and file extension. So let's review that a little bit. So OpenVMS has this hierarchical naming convention with device, directory, subdirectory, file name, file type, file version. Let's break them down. They're easy enough. The device is where the file is located, the volume where it's located. if you don't put it in there, you go to your default device, right? You just like the directory specifies a folder path with nested directives separated by periods. My project and the Samba version. I think this is an example I took from Google somewhere. But the file name is the name of the file, and from a VMS perspective, we always kept this method of extension of the file name extension, the type of the file. So you had your C program was .c, and you compiled and it became a .obj, and you linked it at .exe. But you can run test.dat if that's what you make the linker output be test.dat. You can run it, right? The exe is handy, but not the type is handy, but not a requirement. As in Windows, which says I can't trust this stuff. Yeah. But we know we don't like. The version number is a number that identifies the file version separated by a semicolon in the display, and the version is what makes VMS special and good for. We love our versions, don't we? And we love
yes, we do.
to go back to make an edit. We don't have to do it.
I made Sector 7 go define versions, because up until I pointed out they didn't do it.
They didn't do version, yeah.
He said,
And
"Damn
then,
it."
so that's gonna, from the other talk, the XDE environment, they don't do version because the files actually live on a Windows file system or Linux file system. So that's going to be hard to get used to. Where when you start to, what I would do is I write my C program. I'll probably call it with the date in there. This is the version that I had yesterday and the version I had last year or something like that. We'll have to live with that. I was just ODS2. The file names are not case sensitive, as we know, and even if you type in my file.txt in lowercase, it's saved as and it's the same as.
You may want, for the purposes of the recording,
Yeah.
the limit of the version number is 32.762.
Yeah.
And it won't create a new one.
And it won't create a new one. There is an example on a slide coming up to show that number. Indeed, won't create a new one, and that can be an operational downtime experience. I still remember files 11 ODS1 when the Andy document, and the file names were 9.3, right? Nine bytes for the name. And 9 and 3. Do we know why that was? Because the answer is the storage. The name was stored as radix 50, and the 50 is octal, so really it's 40. 40, so 26 alphabet, 0 to 9 numbers, and $1 and a dash. So that was 40 separate characters stored in, and you could store it in a compact format, not even in zones of bits. And we could, if you then do 40 times 40 times 40, that's 64,000, which is just under 16 bits. And so we could store 3 characters in 2 bytes rather than. And we worried about that stuff back then, right? Yeah. We worried about that
What's
stuff.
What's funny is the accounting file.
Accounting,
yes. And shutdown.
Yes, yeah, exactly. And then update also, I think. No, what was it? Install. VMS install has 1L, I think. No?
Yes.
Yeah. Yes. Silly stuff. That still carries this 9 bit. To this date, we are stuck with decisions made to save 2 bits.
Yeah.
Way back.
There's still some of that in x86 where they've carried that over.
Amazing, isn't it?
Yeah. Maybe that's why they're thinking of a whole operating system.
Now let's stick a real file in there, DKA 100, Hein data test of that. The DKA 100 is the disk drive. So the disk drive would have had physical blocks going from 0 to however big the disk is. Once it's initialized and mounted, we associate it with an XQP processor. That's the in-memory, the activity, the code that supports it. And at that point, we start to talk about virtual blocks within the file, right? So that's the transition again from device to mounted volume. The directory, the top directory appears to be Hein, right? Why not? But really, do we all know that that's not the top directory?
Right.
The top directory is 0000. Again, a historical thing. That's when the directories used to be UICs only, octal only, and the root was 0,0, if you like, right? So then, which got exposed as 00 root. The root, and this will come back and will come back. The root contains itself as a starting point. We have to start somewhere, and it contains my directory Hein.dir, which now appears as the top directory. Next comes my data subdirectory file, which is a directory file inside the Hein directory. Those directories are files in their own right. They're nothing special. They're files with the special contents, but they are just RMS files. You can play with if you want to take your life in your own hands. That same directory Hein I could write the same file spec as 000.hein.data. That would work. You wouldn't, but you could. The file name was test, the data type was that, and the version was 5 in this simple example. How does the system? This is the big one. I'll have a second version of the slide. How is the system now going to find my file in this system, in this organization? So where we go from physical blocks on the disk from 0 to infinity to these is the mapping is going to go through a very special file called indexf.sys, and it contains something very special called file headers. I'm going to explain more on file headers. The file header kind of maps the name of the file to the file itself to the blocks on the disk. I still need to know where to start. So the good part is the indexf.sys starts at block 0 in the logical block space. So at least we know where to find indexf.sys. And then in indexf.sys, we have these file headers that point to the next steps, and there are a handful of reserved file headers. Indexf.sys is its own, says, I am the first file on the system, and I live here. And for intent of finding our data file, we have to go to the root directory 00, which always is the 4th file in the indexf.sys. So now we know where to start. We find we just read the first blocks of the disk where we find indexf. We find the 4th header in indexf.sys, and indexf.sys will now point to where the actual data is in physical storage for the root directory. Are you with me there? So there is an entry here, 00.dir. If I read the data that's behind there, I will find the contents of root directory. Now, that root directory expanded over here on the left side of the picture. On the root directory has entries for itself and any other directory you put in there. So here I finally find my Hein.dir. My Hein.dir doesn't mean a thing yet. It has some file ID, which makes me jump to the right mapping block in the indexf.sys, which allows me to find the contents of my directory. Where I find data.dir, I'm not done yet, because now I need to read data.dir, which then has an entry for the file I was actually after. And now I can go to test.dat with some file ID, and it says, oh, I have 32 blocks over here and 16 blocks over there. So now I can see, oops, 32 blocks here, the beginning of the file, some data. I get to the end of these two clusters, and I need to see what's the next chunk of the file, and I'll jump to the end of my file, which doesn't have to be next to it. It could be anywhere else on the disk. That's your infamous file fragmentation, right? So the system has to do quite a few steps to get there. Now, I threw around quite a few. I talked about file headers already without having explained them, so we'll have to explain them.
It doesn't use the x.y.z format to find the file IDs.
Yes, it does. Well, no. The only thing that matters is the file ID is the first the first
Location.
really only the four. So the file ID, I don't think I explained that, is if the file is the location in index F11, and the version, how many times that location has been used. So if the file was replaced by something else, you cannot accidentally use the next file that's sitting there with the same number, because it's already, if you try to remember file IDs or make them up, then you will be stopped by a mismatch in the sequence number for the file. And the third part is the relative volume, which I will have a demonstration of. I was still in that file naming, and I think I need to reorder these slides. But so I gave you already an early indication of how to find the file and how much work is involved in finding the data for that file really behind the scenes. You just say type test.dat, right? Behind the scenes, all hell breaks loose. No, it doesn't. And of course, as we are going through this path, we are caching as much as we can, and the next time you type a file, everything is ready to go. Then files have extension, file names have extension. We found our file. I just wanted to give you a little thing about the file names must have an extension, so there will always be a dot in the VMS files, right? There will always be that dot visible when you do a directory. The extension can be empty. It gets tricky because we try to help, and we'll just you type a file X. I should put that example there too. It will say file not found x.list, because if you type something, magically it expects a .list file, which nobody ever uses anymore. .text, .log, .list. When is the last time you used .list? I think that's it. That's yeah. I've not used it much. No matter. The file name can be empty also. The file name being empty also leads to funky parsing. As you've seen, if I make a file that I just copy the null device into .temp, it sits there just fine. Now I copy .temp to A, and I pick up the temp gets carried forward. I create an A.temp, but if I want to go back, I want to go and I want to copy A.temp to .b, which seems like I went one way, I can go the other way. That ain't gonna work because it carries forward that A in the file name parsing. So yeah, it's always fun stuff. But you can play with that. And then the file has versions, and the version component is in the text representation separated by the semicolon. We have versions. This is wonderful. This is what we thrive on, and we love them. That's why we like it as both production and development environment. But there's other tools available that take care of versioning. Of course there are. So in our environment, if you're a Linux person, and you edit a file, the original is gone. In our environment, creating a new file with the same name, just an edit session, it does not blow away the older file. It creates a new file, and you can go back.
That saved me so many times.
It saved me so many times.
It's making me lazy.
It makes you lazy. Yeah, you don't even do backups because it's sitting there. File version are limited to 32K for Andrea. So you can run out of versions, and you may have to resequence your number if the sequence is important with some script or some magic command. We're not talking about that. It's so easy to just creating more log file and more log file, more log file. And the easiest way to figure out how bad your system is DFU again. Well, it's the first time I mentioned the DFU tool, which is no longer on the system out of the box. You have to go fetch it from SCI.
Better now.
But it's great. It works, right? So
It's even better.
It's even better.
It's got more functions.
It's got even more function. Yeah. And it's on x86. They took care of it properly. You can say DFU search for files with a version number with a minimum of 10,000 on my system device. And this is a fraction of what it found. It found hundreds of files on our VMS internal systems because we only manage them when they fall over, of course. And indeed, you see that one file reached the max, and that program won't run no more. I think this is a special one that actually they don't want it to create a new
Create
one.
a new one.
They don't
Correct.
care.
Yeah.
They don't care.
But many of the TCP tools create a log for every activation, and you will run out, right?
Does DFU give you the option to renumber?
I should maybe put a slide on there how to renumber them. Yeah,
Yeah. I
because
have a DCL
it-
script, but
the easiest one is to name them into one directory and then back again, and then because as you rename them, we'll take them from the top and they end up in the reverse. So
Right.
I should make a slide on that. Right, you're right. 'Cause, but most folks do the trickle down thing, right? You take the oldest one and make it one and one at a time in a DCL script. Well, at least I think that's what most.
well, all I'm saying is it would be nice if DFU gave you the option to
I
renumber.
don't think it does yet, right? It might. I highlighted one more item here and it's visible on all the files. All these files say 4/16 or 20/2032. We're only using 4 blocks out of the cluster of 16 blocks that's available. Right? That's that cluster coming into action. I want to touch on files and volume size limits. That's changing a little bit. The maximum size everywhere is governed by the 32-bitness of most counters, right? So the maximum size of an RMS file is 32-bit virtual blocks, and that's 4 billion blocks, which is 2 terabytes. That's the maximum for a file. I have not seen applications seeing that as a problem. Does anybody come anywhere close to a 2 terabyte file at this point? I don't think so.
We have some
Be
100
unmanageable.
100 million block files.
Yeah, but not 4 million,
4 billion.
4 billion blocks. Right. On the other hand, the volumes, and we need to figure that out. The volumes, the architecture limit is only 1 terabyte because we don't trust our unsigned algorithms in the XQP. So we're not treating the 32 bits as an unsigned number, and we can only use the first 31 bits on the older versions. Finally, in 8.4, we finally went through all the occurrences of the LBNs, and 8.4 we can go to the 2 terabyte. Now that is not enough for some customers when you put your backups there, right? Have you actually run out of the 2 terabyte, or I don't know?
We have a bunch of 2 terabyte volumes.
Yeah, and wouldn't you rather have 1 10 terabyte volume and not think about where to place your files, or does it not really matter
I'd
much?
rather not have retarded customers do that. But
Well,
Yeah.
the other challenge with these large drives is the time it takes to do the restore.
yes.
Yeah.
So, you've
Yeah,
got,
if you make a backup of the whole drive,
Right.
then that becomes unmanageable anyway.
Exactly.
So you
Exactly.
may want to keep it small.
And when you go to the cloud and you're replicating that stuff to different regions, and
Then we're talking hours now, or days. Yeah. Yet we've been told in feedback from customers that really the 2 terabyte is a restriction they don't want to think about. They must be doing their backups by directory or whatever they choose to do. So we all know that you can create mount volume sets to add disks together, right?
yeah,
That's a
Yeah.
just found that out recently.
act of desperation, though, with creative that volume said.
yeah.
Yeah.
And doesn't that still get into trouble if the first one gets filled?
So I have a little
It does.
demo examples of how that might work out. You can combine multiple volumes up to a single volume, each up to a single volume limit to create a volume that looks like it's much bigger than that. So let's do that. I like the MD device for my testing to see if it all works, because I don't have terabyte drives available. So, it all takes too long when you talk the actual terabytes. But if you want to see the concepts that work, you use an LD device or an MD device to temporarily have or floppy. And no, you don't have floppies no more. Luckily. So who has not used the MD device? And it's right there. You just grab one, and if you want to see, if you want to play with a directory and think I might lose my file, do it on an MD device first and see if the file is still recoverable or whatever you special thing you want to. Or if you had that program that you want to make sure that when it fills up the disk, it has the right message, then you create a 1,000 block disk and you fill that up rather than a million block disk, right?
So MD is DEC-RAM, right?
I know DECRAM, okay.
Oh, yeah,
I didn't know that.
The DEC-RAM, yeah. That's well, that's the modern
Yeah.
implementation of
Oh,
DEC.
MD's memory disk, yeah.
Yeah, DEC-RAM used to be a separate product.
DECRAM.
How's LD different? Is what I always use.
Module disk, yes.
So LD
I can create one that's 512.
LD has a physical file behind it. MD just is in the air, and if you drop it, it's gone.
And LD,
If you let the magic smoke out, it's over.
Is there a license card for DEC-RAM?
No. That's why I want to show it. It's just there now. It's no longer a product that you need to activate.
Interesting.
So it's really handy. And then you as you create them, they have no size yet, and you tell it to I'll have 1,000 block, pretty please. Create 3 of those. You have to initialize them with each with their own label, and you can then mount/bind them, listing all the devices and listing all the labels, and the system will take care of that. So now, if I show device disk $RAM, whatever I named it in the bind command, I will see 3 individual physical devices behind my one volume. So it's really important to still remember the distinction between device and volume. And each of them has a number of free blocks, not the 1,000, because the file system itself takes some overhead from some control file. Okay. So now that I have that file, I can create a directory on it, and I can copy. Oh, I keep hitting that. It's so close. I can copy a good sized file. They're my favorite for this kind of testing to see what happens if the disk is full or so. Copy allocation equals some number. Copy the null device to a file. /log to make sure that it went to the right device. And I do. Sorry, folks. I keep going on.
You're not the only one that does that.
Every presenter.
It is so
this issue.
tiny. Maybe I should just use my fingers to go there.
I'm thinking about that when I present mine.
Yeah. Just
This
the
is
thing hits your eyes though. But,
Yeah.
so now if I do this was the original setup. I had 900 blocks roughly on each of them. And when I copy the 2,000 block file there, it just starts eating up on the first available, the one with most space. It says, okay, I'll grab 900 here. I'll grab 900 there, and I grab another 200 if my math is right from this, right? Leaving 701 empty. So it's transparent. You just copy the 2,000 block file, and it happens to be fragmented over multiple disks. You don't need to know that. Where it shows up, if I do a dir / allocation and print them out with the file ID, which we haven't mentioned yet, with the file ID so this was number file, the root directory is always version, ID 4. I create some other stuff there on the disk. The reserve files go to 11 or 10. And when the first real file was my directory 12, but you see, I have a file 12 on the second disk. So the directory my directory I created didn't start on my first disk, but it created on the first disk that had the most space, which happened to be, for the purpose of this test, the second drive. And then when I create a file in that directory, it says, okay, now the second disk is no longer the most free disk, so I will create it on the third disk to begin with. Yes, the relative volume number indeed. Yeah, I need to rearrange these slides. It's not the right order.
I don't think I tell new users about
No, it was.
Sure, I totally.
It was just because we had a recent experience with the, I need a bigger one, how do I solve it?
Right,
and,
and today most customers just.
But this should be at the tail end of
Expand
that.
on the storage and then use dynamic volume expansion.
It is kind of interesting that it helps understand these RVNs and the file numbers. So in that sense, I'll figure.
I've used the directory myself when I could change.
Do you know the limit to that? How much? 255?
255 is the volume set limit, and
You
20.
cannot mount all 255
Right.
at the same time.
And the versions go to 16 bits, and the file sequence number. So the sequence number is 16-bit, and the file ID is 24 bits. You can see I tossed out those slides in the middle of the presentation. This is where I should have gone first. The concept of a file, right? What the heck is a file anyway? An organized collection of data. It can be found through your directories, and then the big thing is in the VMS system is it's truly identified by a file ID, a number that defines the file, and whatever name is associated with it, our VMS doesn't care. File ID says this is my file. That's what counts, right? The file is mapped onto so it's somehow the file maps the virtual blocks within the file on the physical blocks on the storage, and that's going to be my mapping pointers going in the file header pointing to the actual storage. And the file has many attributes, the dates and the size and the RMS attributes and the owner protection. All of that is stored in the file header, just disjunct from the file. So the file is one thing, the data is one thing, and the header is another thing, and the header lives in index.sys. A directory is also just a file, but it's a dedicated file that maps the file names to those file IDs, how we can find them back. And index.sys is again a dedicated file to hold all those headers, including itself. The index.sys is not a single long file, because that would be dangerous. If somebody touched the first bit of it, you would lose your entire drive. So it sort of replicates itself in the middle there to be able to survive stupid errors. This is from the Kirby book, the pictures. And the basic concept of file, the file header. What does a file header look like? And so these are literally the bytes and everything else in a file header. That header block, the 512 bytes that consists of the header block, has of course the file ID where it's living. It has the RMS attribute area. It has all the basic protection, the owner USC. All of that is stored in the file header. It has a block with all the dates in there, a chunk of data with all the dates in there. These blocks can be at different offsets based on the length of the file name and stuff like that. And then the most important part really is it has a collection of mapping pointers, of which we have 6 formats or something like that. But essentially, the mapping pointer says, I have so many bytes, so many blocks of data at this location on the physical disk. And the mapping pointers can be only 32 bits, and they can be 64 bits as indicated here. So that's the file header. And then the directories, I said, is just another file. And it is just another file in RMS terms. Sequential file, contiguous, variable length, no carriage control, no span. So it doesn't type very well, because it has binary data in there, so it doesn't type at all, right? Each record in the directory starts with the length, a file name, a version, and a file ID. And that's where the magic is going to happen for your multiple files, is there is only one record with the file name, but it has an array of version, file ID, version, file ID, version, file ID, okay? So the initial part of the directory record is simple. We have a size, we have the name, and then it's followed by an array of version numbers and file IDs to find the actual file behind it. So multiple versions do not have a in their own directory records. They just keep on going. They will fill up a block eventually, right? And will repeat the file name in the header of the next block and the next block if you have thousands of them. Oh, it goes pretty quick. So this is 8 bytes there, the version 8 bytes, 512 available, like 400 files, and you need an extension record for to keep track of all your versions.
And I verified that DFU from SCI does have a reversion command added.
Perfect.
Oh,
There is a reverse.
Cool.
Good. I'll put that in the set to see. See, this is a good thing we're doing this presentation here and now. So I'll put that in there also. We know this now. Directory records are kept in order by file name, but that has major implications because it's not an indexed file of any sort. It's just a linear file. So if I have to keep them in order and have to insert something in the middle, something has to give. I have to slide over the high end of the directory, create an empty block, put in a new version, new file, and now I can go forward. Good news is once I created a new block for one new file, that same block is still available for other files with similar names. Right? The inverse happens too, and that's the pain of the delete star.star. When you delete a file, eventually you'll get rid of the block allocated, but you'll also get rid of your directory entry for that file. And eventually the directory block that holds the directory entries empties out. So now you have this empty directory block. And what does the file system do? It compresses all the data beyond the empty spot down away, moving, back in the day, a block at a time. Now, if you do a delete star.star, and your files are A through Z, which one is it going to delete first? It deletes A first, right? That's the first one it finds. So now you delete A, B, C, and I have an empty block, and I shuffle down D, E, F, all the way down to the beginning of the directory file. And it delete 3 more, and I shuffle down the rest again. So we have an n-square problem there. The bigger directory, the worse it gets, and the slower it gets. Since probably 6.0 or maybe 7.3, the default move is 16 blocks. I think you can. Oh, there it is. The ACP max read, the 32 default now, but you can only make it 64. So this kind of says your directories really shouldn't be thousands of blocks. That's going to hurt.
And when you delete, then reverse Cornwall.
And if you have a chance, write a little script and delete in reverse order. Yeah, absolutely. And then the final implication of, because the directories, to make that move easier, to make sure the directories itself is not all over the place, directories are made contiguous, which is fine, except it can lead to surprises where you try to add a file on a disk and it says device full, but it wasn't that it was full, it didn't have enough room for the directory, contiguous room for the directory. That can be, we've all been hurt by that one.
Use like DFU and make that directory.
Yeah. We can make that work. Directories are hierarchical, but we have to have our starting spot, and the starting spot is the master file directory. It's the 000 again. Can't repeat it enough, because we have to understand that concept of the 000 file. It is contained in itself. It has a special file ID such that we can even find it if we didn't know where its directory was. So it is the 4th header block in the index F, and you can, if we do a directory of the master file directory, you see all those reserved files that we talked about a little at this point in time. The master file directory itself, the index f.sys itself, and onwards.
the record allowed 9 levels.
I think we're allowed 9 levels. Did we ever change that? No,
I don't think we
8 subdirectory levels. Yeah. That's a good. That's probably something to add to that. To that presentation as well. Okay, it's almost time.
Excuse me, I gotta go to the next.
Please.
I will put it in.
Thank you. Then a little detailed view of that in the index f.sys. Way too deep for now. We're not going to go in there. And that same picture that we presented earlier might make more sense now, how we map the file name to directories to blocks on the disk. And we'll leave it at that.